Hello everyone! Today we are going to talk about using partial fractions to evaluate finite sums and infinite series. Solving such questions, as we all know, sometimes can be very annoying. First, we need to plug in n equals to 1, n equals to 2 to a very large number. And after that, we also need to find the common denominator, which is very annoying and complex. So to get rid of this, today we are going to learn about partial fractions. It will make the questions more easy. So what is partial fraction? Let's begin with this. Here's the theorem. We have a fraction like this, and its denominator has been factorized. We have fraction like this, and its denominator has been factored. Then we can write this in this form. Divide the fraction into some small fractions. Then we can calculate a1, a2, and as. This is called partial fractions. We also noticed here's a qx. What is 4? Well, qx can be a constant or a polynomial. If the degree of f is, which is the upper part of the fraction, is smaller than s, then it is a proper rational expression. So the qx is 0. If it's not proper, namely the degree of this is bigger than degree of this, namely the degree of this is bigger than the degree of the denominator, then we can use long division to get the qx. After that, we can do partial fractions. As for a1, a2, as, here they are constants because all of them are proper rational expressions. The degree of the denominator is 1, so the degree of the upper part can only be 0. So in this case, a1, a2, as are all constants. But if it's x squared minus something or plus something, a over this, it can be 0 or 1 is degree. Please make sure they are proper. They are proper. Yeah. Okay, next. Let's begin with this problem. Evaluate the finite sum of this expression from n equals to 1 to 5. Seeing this, we might just plug in 1, 2, 3, 4, 5 and add them to get the answer, but it is very complex. So let's recall what we have learned. We have a fraction like this, and we can write it in this way. So let's try this. First, check if it's proper. The degree of the upper part is 0, and the degree of this is 2. So it's proper because 0 is less than 2. Okay, we can continue now. So we should divide it into 2 parts. A over n plus 1, b over n plus 1. This is called partial fractions, but it's not the final form of this. We must guarantee this guy is equal to this. So we should get it back to the original form. n multiply n plus 1. What's the a? So the upper part will be a n plus a plus b n. Okay, since it is equal to this, a n plus a plus b n is 0. Is 1. 1 plus 0 n because it don't have n. So n implies a plus b equals to 0, and a is only constant is 1. So b is minus 1. It's easy to see, right? Then let's just plug in a and b into the expressions we have done. This should be minus, I think. Okay, this is the outcome of partial fractions. So why we need this? What can it do? Or let's say, can it make our calculation easier? It is 1 over n minus 1 over n plus 1. Let's plug in. We don't know what to do, so we just plug in. 1 minus 2, 1 over 2, and plug in 2 is 1 over 2, plus, minus 3, 1 over 3, and 1 over 3 minus 1 over 4. Do you find something special? This is minus 1 over 2, and this plus 1 over 2. It can cancel. This one also cancel. And if we continue writing, it's plus minus 1 over 5. What's the last term? The last term is plugging 5 is 1 over 5 minus 1 over 6. Cancel. At last, we just have 1 minus 1 over 6. So the answer is just 5 over 6. It is much easier, right? Then just plug in 1, 2, 3, 4, 5 and add them all. So as you can see, using partial fraction can make the calculation very easy. Okay, let's move on to the next question. To evaluate the infinite series 1 to infinite. Wow, to infinite. If you just plug in 1, 2, 3, 4, 5, 6 to the infinite, that's impossible. But using partial fraction, it can be very easy. Let's see what we have here. It is first check whether it is proper. The degree of the upper part is 0 and the degree of this is 2. So 0 is less than 2, so it's proper. Okay, we can move on to the next step. It's n plus 2. So let's do what we have done before. N a over n plus 2 over b. Okay, and get it back to the original form is an plus 2a plus bn. Okay, they should be equal, so an plus 2a plus bn is 2 plus 0n. It implies that a plus b is 0 and 2a is 2. So a equals to 1, b equals to minus 1 again. And we can plug in. Then we get the expression is equals to 1 infinite 1 over n minus n plus 2. Okay, let's just plug in 1 because we don't know what to do. So we just plug in and find the pattern of the constellation if it have. So plugging 1 is 1 minus 1 over 3, and plugging 2 is 1 over 2 minus 1 over 4. Oh, sorry. 1 over 4, and plugging 3 is 1 over 3 minus, well, here you can see, whoa, it can't cancel. Is the formula wrong or something? You can see it can cancel here, but here it can't cancel. Don't worry, just continue plugging. The 3 minus 5, 1 over 5. Oh, then you can see this one can be cancelled by this one, but we are not sure. So continue. 1 plug in 4 is 1 over 4 minus 1 over 6. Oh, this one can be cancelled. So we find the pattern. So let's just skip this to the infinite. Infinite. It is n. Let's plug in n minus 1 first. N minus 1 minus n plus 1. N 1 over n it minus 1 over n plus 2. Okay, let's cancel. You may ask why it's cancelled. You can just refer to the previous term. It is. So cancel. So at the last, we only have 1 and, oh, sorry, it's 1 and 1 over 2 and this 2. We add them together. 1 plus 1 over 2. Oh, please don't forget the sign. Okay, so this is minus n plus 1 minus 1 over n plus 2. All right, this is the final answer. It's quite easy, right? So let's move on to the third question. Oh, sorry. First is finite, 2 to 8. And then first check whether it is proper. It's 0, it is 2, 0 is less than 2, so it's proper. We need to do the long division to find the qx. Find the q. Okay, then do the same thing as we have done. Minus n plus 1 and get it back to the original form a, oh, sorry, this is plus. An plus a plus bn minus u. You can just calculate it since they are equal. So an plus bn plus a minus b should be 2. A plus b plus 0 and half should be 0, and a minus b should be 2. So we can get that a equals to 1 and b equals to minus 1. And plug in this, plug in to the original expression. 1 and minus 1, minus 1 and plus 1. Okay, then let's just plug in 2. Plug in 3. Plug in 4. You see, it can cancel again. Cancel until 8. But you may have a question, why can they cancel? And what's more, it's quite similar to what we have done in this problem. So let's make a comparison. This is what we get in this problem. This is what we get in the previous problem. What's the common point between them? Because they illustrate the relationship between the previous term and the next term. Let's say, for example, if we plug in n prime plus 2, n equals to n prime plus 2, let's see what will happen. Then this 1 over n became n prime plus 2. It's just like this one. So you minus this, you minus n plus 2 in this term, and then you can add it back, n plus 2, later. That's why it can be cancelled, because it illustrates the relationship between terms. You minus 1 and you plus 1 later. That's a principle of partial fraction in this application. Since the calculation is the same as the previous one, so we just skip it to next one. Evaluate the infinite series 1 to infinite. Oh, this one haven't seen before, but that's okay. First, check whether it is proper. Degree of the upper part is 0, and the degree of this is 2. 2 is less than 0 is less than 2, so it's proper. Okay, then let's factor this. 2 n plus 1. This should be 1 because they should be equal. Whoa, this one seems a bit weird because we can't build a relationship between 2 and n plus 1. What should we do? Just 2, so we can just take it off. See, it's easier. Then we can just do what we have done before. A over n plus n plus 1 over b over n plus 1. And that's the same as what we have done, right? So we just need to get the a and b and continue plug in and cancel, then get the final answer. I know cancel is it feels very good to do the cancellation, but please don't forget the 1 over 2 after you cancel. Okay, don't forget 1 over 2. So it's just skip the calculation. Okay, this one. Oh, degree 3. Degree 3, degree 0. 0 is less than 3, so we needn't to do long division to get the q here. Okay. Then what we should do is to factorize this to use partial fraction. n squared minus 1 over 3 over 8. And we can continue n minus 1 and n plus 1. Oh, here are three factor. We haven't seen that. What should we do? Don't be afraid of it. Just do what we can do. Fact, using partial fraction, a b over n plus c over n plus 1. All right, then we can calculate get the ABC. Let me just give you the answer because it's not that hard. The expression after partial fraction is plus minus n plus 1, and then we plug in. Because we don't know what to do, just plug in. Find the pattern of cancellation. Just stare out if it doesn't work. Plug in 1 is plus 3 over 2 minus 1 over 2 minus 3 over 4 plus 1 minus we still haven't something special here. So continue. It is minus plus minus. Do you find something special? Let's continue. Oh, I have found one. You can see minus 1 over 2, 1. It can cancel. You can see this one and this one. It can be cancelled. Well, I think we have found the pattern of cancellation. So we just skip this. Alright, we just plug in 199 first. 199 minus 2, 198 over 3, a 3 over it, and 3 over 199 minus 2 multiply 200 and then plug in 200 to multiply 199 plus 200 3 minus 201 hmm, 2 plus multiply, and we can just cancel, find the cancel. Okay, then we have these three term and these three figures. So just add them together. We got the final answer. And there is another rule you might find that after cancellation, the distribution of what we need to add, or let's say at last what we have, is symmetric. It's just a skill. You can just do the cancellation and find it, or you can use it to find the symmetric position of these figures. If you don't understand, just cancel. Okay, next. After seeing this, I think this is not that hard, but let's check whether it's proper. It's 0, it's 2, 2 is 0 is less than 2, so it's proper. Let's do next step. Next step, we need to partial fractions. So we need to factor this first. It is 2n minus 1, 2n plus 3, 1 over it. Well, this one is different from what we have seen before, but we can tell that it shows a relation. Let's divide them first. Divide them into two parts first. 2n minus 1. Oh, this should be a plus b 2n plus 3. And we find the ab. Let me just tell you the answer. A equals to 1 over 4, b equals to minus 1 over 4, and we just take out the 1 over 4, you know? It can make the calculation easier. 2n minus 1, this should be minus, and 2n plus 3. Okay, then this expression is our expression after partial fraction. Okay, let's see whether it can cancel. But we can check it. I have said that if it illustrates the illusion, I have said that if it illustrate the relationship between the previous term and the next term or next terms or that is that's not gone. It can cancel anyway because you can minus this and add this back later. So let's see whether it can do it, whether this expression can do that. We let n equals to n prime plus 1. Just check. This is needn't you needn't to write this in your this is just check. Tell you tell the part pattern why it can just this is just check. Telling you why it can cancel. We plug in n equals to n prime plus 1 to n plus 1 is not equal to it, then we can plus 2. Next term, you can find that it's equals to 2n prime plus 3. Just equal to it. So it can cancel. And what's more, it's the same form like this. It can cancel with this, but it can cancel with the next term. Next column, next row, yeah. So we can find the pattern now. So rest of things is easy, but please don't forget the 1 over 4 after cancellation, okay? So we just skip, so we can just skip the calculation. The final answer is 1 plus 1 over 3 plus, it should be minus 2n plus 1 over this, and minus 2n plus 3, 1 over it. And don't forget 1 over 4. This is easy to forget. Okay, let's move on to the next. Whoa. Oh, here's and we haven't seen that. Let's see. Evaluate the finite sum. Finite sum. Oh, it's to n. Okay. Let's write. Check whether it's proper. Upper side, upper part, degree of upper part is 1, and the degree of this is 4. 1 is less than 4, so it's proper. So we can move on. Let's check whether it's proper first. It is the let's check whether it's proper. The upper part of this is degree of this is 1, and its denominator's degree is 4. So 1 less than 4, so it's proper. We can move on to the next part. Next part we need to I think we needn't to do the factor because n squared is it is just the purest term of n plus 1 squared. So we needn't to do the factorization, I think. Just divide it into two parts. and get it back to the original form to find, oh, sorry, to find what A and B. A and B are. So A equals to 1, B equals to, let me check. B equals to -1. And then we plug in A and B to get the expression after partial fraction. 1 over n squared minus 1 over n plus 1 squared. Okay, that seems quite easy. Let's do the calculation. 1 minus 1 over 4 plus 1 over 4. Wow, this can directly cancel. So I think we already find the pattern of cancellation. So let's skip to the end. Let's plug in n minus 1 first, okay? N minus 1 squared minus n squared 1 over n squared. And the last term is n, oh, that's okay. I remember this is 1. We cancel, 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 cancel. And we have, this is n squared. All right, I will rewrite the expression here. Plus 1 squared. And the last term is just n squared 1 over n squared minus n plus 1 squared. And cancel, cancel, cancel. This is canceled. So only these two numbers are left. So 1 minus n plus 1 squared is, oh, n plus 1 squared is just the final answer. Okay, let's move on to the last question. Okay, this question, wow, it has 4 terms. Well, I think it's also annoying, but not that annoying using partial fraction if we do as a stereotype and with a stereotype like a b over n plus 1. Oh, we should check whether it's proper. It's 0 and degree of it is 4. So, okay, that's proper. We can move on. Plus 3 c over n plus 2 plus 4 cd over n plus 3. That seems to be easy, but still annoying. Can we find something some way more easier? Then we can try this. I have said that we want to find a relationship between the purest term and the next term or next two and that's not gone. Here we have this. How can we find the relationship between find a or let's just say how can we find two terms that one term is a purest term and the other term is the next term? Let's try. If we choose this, then it should be n plus 1 and this one is next. This one is the other one plus b n plus 2, n plus 3. Let's check. We plug in n equals to 1. N equals 2. N prime plus 1. N, so we plug in this in this lah. It is n plus 1, n prime plus 2. We can see it's not equal to this. Alright, then if we just plug in n prime plus 2, so if we plug in n prime plus 2, we can get plus 2 plus 3. It's just this. It can work. Then can we find another way that we can that illustrate this relationship between the purest and the next term? This one is okay, but I think there should be another easy way. What if we choose this? n plus 1, n plus 2, a over a plus n plus 1, n plus 2, n plus 3, b over a. It seems a bit complex, but let me tell you, it is quite easy. It's just check. You needn't to write it in your paper on your paper. Let n equals to n prime plus 1, and you can see it's just n prime plus 1, n prime plus 2, n prime plus 3. See, it's equal. N prime n. Huh. I mean, this using this, we can know that this is just the purest term of this of this uh of this guy. So this one is okay. It's also okay. Let's get it back to the original form. n plus 1, n plus 2, n plus 3. To get back to the original form, we need to multiply n plus 3 up and upside and this side at the same time, because we need to guarantee it the figure, because we need to guarantee it will not change. So we need to multiply n plus 3 up and down. As for this, we need to multiply n. Then we can an plus 3n plus bn. This guy is equals to this guy. So an plus, oh, what's this? It's 3a. Yeah. Plus 3a plus bn equals to 0n, and 3a equals to 1. So a equals to 1 over 3 and b equals to minus 1 over 3. That's quite easy. Let's write it again. After partial fraction, this is Let's take out 1 over 3. 1 over 3. Oh, okay, this n plus 1, n plus 2, n plus 3. Okay, then let's just plug in 1, 2, 3, minus 2, 3, 4. And continue plug in 2, 3, 4. Minus 3, 4, 5. Okay, we can cancel. We already find the pattern of cancellation. So let's just find the last term. The last term is n plus 1, n plus 2, minus n plus 1, n plus 2, n plus 3. This one is cancel. Then we only have this one and this one here. 1, 2, 3 is 1 over 6 minus this. Don't forget the sign, huh? Don't add it. 1 over n plus 1, n plus 2, n plus 3. And don't forget the 1 over 3. At the very last, don't forget it. So this is the final answer. Well, as you can see, partial fraction is very useful in solving this kind of problems. Hope you can learn a lot after this class and try to use this formula yourself. Not formula, try to use partial fractions to solve this kind of questions yourself. Thanks for watching. See you next time.